Today we'll start the second method, moment distribution method. So already you know how to solve the continuous beam or frame, that is sway and non-sway by slope deflection method. And this is also one method. So using this method, you can solve the continuous beam and also the portal frame. Coming to introduction, this method is suggested by Professor Hardy Cross in early 1930. So it is also known as Hardy Cross method. So this method, you can analyze the statically indeterminate beams and frames by simple hand calculations. In this method, solution of simultaneous equation of slope deflection method is replaced by iterative distribution procedure. So this method is basically based on iterative process. You know, in any continuous beam or frame, at each joint, that sum of the final moment is equal to 0. You know, in the slope deflection method, but here you see, so this is one method. Here you have to solve this by iterative process. So this is the procedure. So in this method, artificially restraining temporarily all the joints against rotation and write down the fixed moments for all the members. Like any continuous beam, you have to assume all ends are fixed, that is all ends are artificially restrained temporarily, and you have to find out what is the fixed moments. The next procedure, the joints are then released one by one in succession. Then at each release joint, the unbalanced moment are distributed to all the ends of the member meeting at the joint. A certain fraction of these distributed moments are carried over to the far end of the members. So these distributed moments, what you have distributed the moments to the end of the member, and that moment that you have to carry over to the far end of the members, some fraction. So what is that fraction? That fraction is your half. So half of the moment that you have to carry over to the far end of the members. Then the release joint is again restrained temporarily before proceeding to the next joint. First you have to make unrestrained. After distributing this moment, then again you have to take that restraint temporarily before proceeding to the next joint. Then you have to go to the next joint, and in similar way, so that next joint should be unrestrained. Again you have to balance that unbalanced moment, distribute to the end of the member which is meeting at the joint. Then again you have to carry over to the other end. Half of the moment is carried over to the other end of the member. So this same set of operations are carried out at each joint till all the joints are completed. So this type of operation you have to carry out at each joint of the continuous beam till all joints are completed. So this complete one cycle of operation. So similar way, iterative for a number of cycles till the values obtained are within the desired accuracy. And you have to take the sum of the moment. You can find out what is the final moment using this method. So this is totally the iterative process. The unbalanced moment that you have to distribute, then you have to carry over to the other end. Then again you have to unrestrain that another joint. Again similar process you have to do. This way you have to continue. So you will get the desired accuracy. Let us coming to the what is absolute and relative stiffness of the members. The absolute stiffness of a member can be defined at the moment required to produce a unit rotation at the simply supported end. So here you see, so this support is your simply supported and this is your fixed. So it is the moment required to produce unit rotation. So for unit rotation, what is the moment required here? So this is your called the absolute stiffness of a member. What is the moment required to produce unit rotation? Means theta is equal to 1. So what is the moment is required? So this is called the absolute stiffness of a member. MAB is equal to absolute stiffness of a member AB when theta is equal to 1. When theta is equal to 1. But you know, so due to this rotation, what is the moment? MAB is equal to 4 EI theta by L. You know, at near end 4 EI theta by L. But here the theta is equal to 1. So 4 EI by L. Similarly, the moment at the further fixed end MPa, what is the moment here? The moment here is equal to 2ei theta a by L. But theta a is equal to 1. So MPa is equal to 2ei by L. So due to this unit rotation at 1, so what is the moment here? MAP is equal to 4ei by L. And what is the moment at the fixed end B? MPa is equal to 2ei by L. Then, so what is the relative stiffness? The ratio I by L is in equation 1 and 2 is known as the relative stiffness. You know the moment of inertia by length of the beam. So this is called the relative stiffness of the member. So this is denoted by K. So for any prismatic member AB, the relative stiffness KB is equal to KPA is equal to IAB divided by LAB. The moment of inertia of span AB divided by the length of span AB. So this is the relative stiffness of the member. So now you are clear what is absolute stiffness and what is the relative stiffness. So absolute stiffness of a member is defined as the moment required to produce unit rotation at the simply supported end. And what is the relative stiffness? So this is the moment of inertia of a member divided by the length of a member. The ratio is called the relative stiffness of a member. Then what is carryover factor? See, if a moment MAB is applied at end A, so this is the moment at the end A of the member in figure 1, a specified amount of moment MPa is generated at the further restraint end. So this is the moment generated at the further restraint end, fixed end. The carryover factor is defined as the factor by which the moment at simply supported end A, MAB, is multiplied to get the moment carried over to the other end, that is MBA. So this is the factor. So you have to multiply with the MAB and that moment will be carried over to the other end, further end B. So that is your MBA. So MBA is your equal to CAP into MAB. CAP is your carryover factor. Because whatever the moment you are having at A, joint A, MAB, so that moment you have to multiply with some factor and that moment is you have to distribute to the other end. And this factor is called the carryover factor. So MPA is equal to CAP into MAB. CAP is equal to carryover factor. So from equation 1 and 2, we can write, from equation 1, MAB is equal to 4EI by L, and MPA is equal to 2EI by L. 2EI by L. Carryover factor is equal to MPA divided by MAB. MPA divided by MAB. So MPA is equal to 2EI by L and MAB is equal to 4EI by L. What is the ratio? Half. So carryover factor for any prismatic member is your half. The half of the moment that you have to carry over to the other end of the member. Half of the moment. So that for prismatic member, carryover factor is always half. So this half moment you have to carry over to the other end. So let us take if the further end is your hinge. In previous case, the further end was fixed, but here you take the further end is your hinge. For this case, the further end is your hinge. So for this case, so the stiffness, the corresponding stiffness is known as the modified stiffness of a member. So this stiffness is your MAB is equal to 3EI by L. So here the stiffness is equal to 3EI by L. Because if the far end is your hinged, so you have to take the stiffness is your 3EI by L. MPA is equal to 0. Because so and the relative stiffness K dash is equal to 3 by 4 K. So K is the stiffness and K dash that you have to take relative stiffness is equal to 3 by 4 K. So K is equal to I by L, but here the K dash, the relative stiffness is equal to 3 by 4 I by L. When end of the member is your hinged, so this case, so you can find out the relative stiffness of the member 3 by 4 I by L. And the moment carried to the further end is your 0. Here the moment is your 0. Then coming to the distribution factor. So what is distribution factor. So consider a joint. Here you see this is joint in a structure where two or more members meet. So joint. So here how many member meets? 4 member meets. Here how many? 1, 1, 2, 1, 3, 1, 4, and 1, 5. More member meets. If you apply the external moment M to this joint, the joint undergoes a rotation theta as shown in figure. So here you see. So due to the application of this moment M at the joint, this is the deflected shape or elastic curve. So here you see, so what is the rotation takes place here? The same rotation takes place also here, and the same rotation also takes place here, and also the same rotation takes place here. So same rotation takes place at the joint to the corresponding member. And this is the E modulus of elasticity, moment of inertia, and this is the length of the member. So L12, and here this member length is L13. This is L14. This is L15. Similarly, the stiffness EI is your EI12. The moment of inertia I12, I13, I14, and I15. This is the different for different members. Since all the member meeting at this joint undergo the same rotation theta, so already you know that is the same rotation takes place here theta. The applied moment M is distributed to each of the ends of the members according to their relative stiffness values. Then what you have to do? So what is the moment here? What is the moment here? So this moment you have to distribute to end of each member. The factor by which the applied moment is multiplied to obtain the end moment of any member is known as the distribution factor. So this is the factor. So what is distribution factor? Is the factor. So this factor you have to multiply to the applied moment. What is the moment? If you are applied here, so you have to multiply this factor to this moment, and you have to distribute to the end of the joint to 1 here, and you have to distribute that moment to the 1, 3. And you have to distribute the moment to 1, 4, and you have to distribute this moment to 1, 5. So whatever the moment you are acting here, this moment you have to multiply it with this factor, and that moment you have to distribute to end of each member which is meeting at joint 1. And this factor is known as the distribution factor. This, you see the definition, the factor by which the applied moment is multiplied to obtain the end moment of any member is known as the distribution factor. Then coming to this figure, this is the free body diagram of joint 1. This is joint 1. So this is the moment acting here, and the end moment of end of the member. This is M12, M13, then M14, then M15. Let us take the equilibrium of joint 1. So this is joint 1. So what is the equilibrium? Because this is the applied moment, and this is the moment at the end of the member which is meeting at the joint 1. So what is the sum of the moment at joint 1? So for equilibrium of joint 1, we have M12 plus M13 plus M14 plus M15 minus M is equal to 0. Because this moment you are taking positive clockwise, and this is your anti-clockwise negative. So what is the moment? Sum of the moment at joint 1? M12, M13, M14, M15 positive minus anti-clockwise minus M is equal to 0. Then the end moments of members can be written in terms of the angle of rotation. So you can write the end moment M12, M13, M14, M15 as per the rotation. You know that is 4E I theta by L. 4E I theta by L. This is your due to rotation, the moment generated 4E I theta by L. I by L is equal to K, relative stiffness of the member. So M12 is equal to 4E K12 theta. K12 is equal to I12 by L12. Similarly, M13 is equal to 4E K13 theta. So K13 is equal to I13 by L13. Then M14 4E K14 theta. So K14 I14 by L14. M15 is equal to 4E K15 theta. K15 I15 by L15. So this is the relative stiffness of the member. So this you can find out from the moment of inertia and the length of the member. Already we have discussed. Then after getting this M12, M13, M14 and M15, then after substituting this value in equation 7, so this equation becomes M is equal to M12 plus M13 plus M14 plus M15. Then M is equal to, after putting this value here, 4e k12 theta plus 4e k13 theta plus 4e k14 theta plus 4e k15 theta. This is the moment. Then here you take the common 4e theta. Then the equation 4e theta into bracket k12 plus k13 plus k14 plus k15 bracket close. Then M is equal to 4e theta summation of k. Then theta is equal to M by 4e summation of k. So what is summation of k? Summation of k is equal to the sum of the relative stiffness of all members meeting at joint 1. Here, how many members meets at joint 1? 1, 2, 1, 3, 1, 4, 1, 5. What is the sum of the relative stiffness here? Sum of k is equal to k12 plus k13 plus k14 plus k15. That is, you have to find out for individually for each member what is the relative stiffness. Then the sum of this relative stiffness is the relative stiffness of the joint. So then substituting the value of theta in equation 8, we get. So here you see, so this is the theta value you got here. Then you put this theta here in equation 8. Put the value of theta from equation 10 in equation 8. So after putting this one, M12 is equal to 4e k12 into M by 4e summation of k. 4e k12 into M by 4e summation of k. So here you see, so this 4e and 4e is cancel each other. The remaining equation, M12 is equal to k12 divided by summation of k into M. The ratio k12 by summation of k indicates the fraction by which the applied moment M is to be multiplied to get the moment registered by the member 1, 2. So this is the fraction. So this fraction you have to multiply to the moment M, and this moment is you have to distribute to the end 1, 2. So this is the M12. This is the distributed moment. M12 is equal to k12 by summation of k into M. This ratio is called the distribution factors. The ratio k12 divided by summation of k is called the distribution factor. What is distribution factor? The relative stiffness of the member, any member, divided by the relative stiffness of the joint is called the distribution factor. So this is the distribution factor denoted by RAB. So what is the sign convention you have to follow when you are analyzing this method? So you have to take all clockwise moments are positive, then all anti-clockwise moments are negative. You have to take this is the sign convention. Clockwise moment positive and anti-clockwise moment negative. You know that is clockwise and anti-clockwise. Already we have discussed in slope depression method. Then first we will start the application of moment distance method to continuous beam with fixed end. What are the steps, different steps? When you will solve this the continuous beam with fixed end, so you have to follow these steps. So the first step is that is the assume all ends of the beam are fixed, find fixed end moments. This is the first step. Then the second step, calculate distribution factor for all members meeting at a joint. You have to find out the distribution factor for all members meeting at a joint. So for this distribution factor, first you have to find out what is the relative stiffness of a member. Then after getting the relative stiffness of all members, then you have to find out what is the relative stiffness of joints. Then after getting the relative stiffness of joint, then you can find out what is the distribution factor for all members meeting at a joint. Then you can find out what is the distribution factor. because relative stiffness of the member divided by the relative stiffness of joint. So this gives the distribution factor for members. The balance a joint by distributing balancing moment to various members meeting at the joint proportional to their distribution factor. Do similar exercise for all joints. So for all joints, you have to do the similar exercise. So for all joints, you have to find out what is the distribution factor for all the members. So and after getting this that unbalanced moment, so that you have to distribute to the member which is met at the joint by multiplying with the distribution factors. So then what you have to do? Then carry over half the distributed moment to the far ends of the members. Then you have to distribute the half of the moment to the other end of the members. This is your called the carryover. So by multiplying with the carryover, so this is your half of the moment that you have to carry over to the other end of the members. Carry over half the distributed moment to the far end of the members. This upset the balance of the joint. So this is your balancing the joint. Then repeat steps 3 and 4 till distributed moments are negligible. So this step is you have to repeat till getting the distributed moments are negligible. Means so at the end you will get the sum of the final moment that is very equal to 0 at each joint. Then what you have to do? Sum up all the moments at a particular end of a member to get the final moment. Then after getting this final moment, you have to check whether at a joint the moment is your coming 0 or not. Just approximately 0, because this is the iterative process, iterative method. So you will get that approximately just equal to 0. So this is the steps that you have to follow for solving any continuous beam by moment distribution method. Let us coming to question 1. Analyze the continuous beam by moment distribution method. Here you see. So this is the continuous beam. 1, 2, and 3. One end is fixed, and other end is also fixed. And here given 100 kilonewton the load at the midpoint of 1, 2, and here given UDL 20 kilonewton by meter throughout the span. And this length is given 7.5 meter, and this is given 5 meter. And the moment of inertia for span 1, 2 is given I, and moment of inertia for span 2, 3 is given 3I. So first you have to find out piston moments by assuming all ends are fixed. So this is the piston moments: MF12, MF21, MF23, MF32. So here you see the piston moment. This one is your this is the load you are present at the midpoint. So what is the moment here? You know already. You know in slope deflection method. So minus 100 into 5 by 8 is minus 62.50 kilonewton meter. And MF21, this is clockwise. So positive 100 into 5 by 8, this much. And for MF23, so here UDL minus 20 into 7.5 square by 12, minus 93.75 kilonewton meter. And MF32 plus 20 into 7.5 square by 12, plus 93.75 kilonewton meter. So this is the piston moments. First assuming all ends are fixed, and here these are the piston moments. Then the next step is a relative stiffness of the member. So relative stiffness K12, K21 is equal to I by 5, and K23, K32 is equal to 3I by 7.5. K12, K21 is equal to I by 5, and K23 is equal to K32 is equal to 3I by 7.5. This is the relative stiffness of the member. Then you have to find out the relative stiffness of the joint. So here you see. So this is joint. So here, how many member meets are joint to? 2 member. One is a 2-1 and another one is a 2-3. 2 member meets are joint 2. So you have to find out the relative stiffness of the joint 2. K2 you can find out by taking K21 plus K23. You have to take what is the relative stiffness per member 1, 2, and you have to take what is the relative stiffness per member 2, 3. So K21 plus K23 is equal to K2. So here K2 that you can find out the relative stiffness of joint. K21 plus K23. So K21 you know already for member I by 5, and K23 also you know 3I by 7.5. After adding these two, so you'll get what is the relative stiffness of the joint. Then what is the next step? You have to find out the distribution factor. Then you have to find out what is the distribution factor here, and what is the distribution here, and what is the distribution factor here. If the end is your fixed, so the distribution factor is your 0. For fixed and the distribution factor, you have to take this is your 0. And for 2-1, so for 2-1, the distribution factor is equal to K21 by K2. Then you will find out what is the distribution factor here, 2-1. So you have to take K21 divided by K2. Similarly, when you will find out what is the distribution for this one, K23, R23 is equal to K23 by K2. R21 is your K21 by K2. So K21 already you know, I by 5, and K2 is your this one, the relative stiffness of joint. So after this simplifying, so you will get what is the distribution factor for R21 for member 2-1. Similarly, what is the distribution factor for member 2-3? So R23 is equal to K23 divided by K2. So K23 you know here 3I by 7.5. So 3I by 7.5 divided by the relative stiffness of the joint, I by 5 plus 3I by 7.5. So this is equal to 2 by 3. R32 is also 0. R32 also 0. I have not written here R32. So this is also 0 due to fixed time. These are the distribution factor. How we will solve this one? Here you know what is the piston moment, then you know what is the relative stiffness of the member, then joint, then distribution factor. So this is this moment distribution method you have to solve. So just below this, suppose this is the support 1, 2, 3. So here you draw one line, vertical line, and here you draw just below 2 support, draw another line, and just below 3, draw another line. So first you write what is the distribution factor. Draw here one box. You make one box here. Similarly, here you make another box. Here also one box, and here also one box. 4 box. So first you write what is the distribution factor for end of each member, because this is fixed end. So here the distribution factor is equal to 0. And here what is the distribution factor? So this is 1/3. Here 2/3, and here 0. So first you write what is the distribution factor. Then you write what is the fixed end moments. You got here what is the fixed end moment, minus 62.5 plus 62. So here just to write what is the fixed end moments. Then what you have to do, because what is the unbalanced moment, you have to take, this is the joint. So here the unbalanced moment 62.5 minus 93.75. So this is the unbalanced moment. So this moment you have to distribute to this end and this end by multiplying with the distribution factor. So the what is the unbalanced moment? So this moment, the unbalanced, the net moment into 1/3, and you have to put here in opposite sign, because here you will get that the unbalanced moment negative sign, but you have to multiply this to 1/3, and here you have to put in opposite sign. Similarly, the unbalanced moment you have to multiply with 2/3, and you have to put in opposite sign. This is your the balanced here. The unbalanced moment balanced by multiplying with the distribution factor. So this is FPM, then this is your balance. And here you see, so this into 0, 0. And here you see this into 0, 0. Then what you have to do? Then this moment you have to carry over. Half of the moment will be carry over to the other end. So here you take half of the moment to this side, and here you take the half of the moment to this side. And this is your 0. So here this is 0, and here also this is 0. This is your 0. Then after taking this carryover moment, so here there is no iterative process is your that we can further proceed. So what you have to do? Then you have to add these two moments, minus 62.5 plus 5.21. So here this is the final moment. Then here what is the final moment? 62.5 plus 10 point. And here you see minus 93.75 plus 23. You have to add the moments here. This is. But here you see what is the final moment you got here? 72.92 minus 72.92. So the summation of this moment, the final moment are joined to is equal to 0. And here you see here at 104, so 93.75 plus 10.42, this is your 104.17. So this is the final moment. So you have to check always, this is your this should be 0. And also you have to check the sum of the distribution factor at each joint is equal to 1, because at joint 2, so this is the distribution factor for this member, and for this member this is the distribution factor. So you have to always check the distribution factor at the joint 2 is equal to 1. The sum of the distribution factor should be 1. So this is the moments, the final moment. This is the final moment. So after getting the final moment, then you have to give the duration of the moment. Then you can plot final bending moment diagram. Then also you can plot the shear force diagram. So we'll stop here.